So, yes, analyzing real-world networks in Wolfram language. What will we be discussing today? So we're going to start with a very brief introduction to what is a graph, what is a network, and then how we can build on that definition to tackling problems in the real world. Okay, there's a couple of brief definitions you'll need to know before you go any further. Okay, we'll also investigate some basic measures of graphs and networks, such as density and reciprocity. And then we'll investigate finding communities and cliques within a graph with varying strictness on how one might define a community or a clique. We'll talk about various paradoxes that arise when you're dealing with graphs of varying degree, and properties like homophily, assortativity, centrality. And then we'll look at some really interesting examples associated with finding the maximum flow through a network and also the minimum cut. Okay, there are these famous network theorems associated with these, and we'll see how to implement these in Wolfram language. Great, okay, let's get started. So here we've got the basic definition of a graph. Now, maybe you're used to hearing a graph in the sense that something that is plotted on X and Y axes, but that's really a plot. And if you want the definition for a graph, you go a bit more abstract, and it's a collection of vertices and edges, or edges and nodes. Nodes and vertices are sometimes used interchangeably. And a graph is defined as a set of vertices along with a set of edges that connect these vertices. Okay, here is how an example of a graph looks in Wolfram language, and you can click here to see the code that generated this. So this is an example of a graph called a Peterson graph. Okay, typically these vertices or nodes represent some entity, and the presence of an edge indicates a relationship between entities. Okay, vertices could be Facebook accounts, and whether two accounts are friends would be indicated by an edge between them. So you can see straight away we can go from some abstract collection of edges and vertices, and we've got a real-world network. Okay, next definition is a directed graph. So this is what you get when relationships are not necessarily reciprocated. Okay, you need to indicate this by a directed edge on the graph. So the arrow here is pointing from this vertex to this vertex. And the real world example for this is Twitter account A might follow Twitter account B, but B may not follow A. B might not follow anyone at all. Okay, so we've got the same graph, or the same collection of nodes and edges, but in this case, some of those edges are directed. Again, here's the code for this, where we've actually just specified random directions by using this directed graph function on the same undirected graph we had before. Okay, now, so we've got graphs, directed graphs. Now let's look at networks. So here we've just assigned some random numbers to the nodes and edges. Okay, the red numbers are at the nodes and the black numbers are at the edges. So what we say when we do this is that we are weighting the edges or annotating the nodes. Okay, so here the weights on the edges could represent some kind of indicator of traffic, like 30 messages. Yes, so you can see, you can think of lots of different quantities that could represent the weights of edges on a network. We'll look at an example later on, which is a railway network, and the edge weights are in the edge weights represent how much oil or something can be transported on these trains. Okay, so we call this type of graph a network, and the art of drawing insights from a network is network analysis. And today we will see why Wolfram Language is your go-to tool for this network analysis. Okay, you need look nowhere else. Okay, great. So we've got the basics down, I think, and I will just briefly show you how you could construct a graph of your own. We'll have some directed edges and some undirected edges. So we just use the graph function, and then I want the first node connected to the second node connected to the third node. Okay, very simple. Okay, and in the notebook, this is just the best representation of these vertex and edge connections. Okay, so let's look at, if we change one of these directed edges to undirected edge, let's say this 1 to 3. So we just type escape, UE, escape. That's just the convention for undirected edges. And we run this again. Okay, so the graph has actually changed shape because now we no longer have an arrow between these nodes. Okay. So essentially what's going on behind the scenes is that the kernel is interpreting how best to visualize this graph in the front end. Okay, we have a question from Ajit. How are weights and annotation distinguished in your graph? So I believe I'll just talk about this one. I'll show the code for this. So we've taken this graph that we had before, the directed graph from the previous slide, and we define an edge weight that is a random integer between -5 and 10. And then we also have vertex labels that are some random integer between 10 and 20. Okay, so the vertex labels are really just labels. And then we specify their style with vertex label style, for example. Here we're just indicating that we want to label the edges with their weight, which is defined here. Okay, hopefully that helps. Ajit, thank you for your question. Okay, now before we get into the real meat of this talk, I would like to say I'm giving a webinar on just purely networks and graphs on the 18th of December. And in that webinar, I can go into a bit more of the basics of like how we construct graphs in the Wolfram language. But I can't really do that today because I wouldn't get through the content. So I can't linger on this for too long. But as a kind of sneak peek of what will happen in that webinar, we'll be looking at functions like this find spanning tree. So if I had to bring up the documentation of this, you can see that take a graph G with vertices 1 to 8 like this, and find a spanning tree of G ensures that all vertices are included in that tree. Okay, so it gives a tree containing all the vertices of the graph, but not necessarily all the edges. Anyway, there's lots of functions like this, and we'll be looking at those. But today we'll try to focus on real world networks. Okay. So how do we get these networks and graphs into the notebook so we can draw some insights from them? Well, there are lots of graphs available directly from the notebook itself, and they're all kind of stored within this graph data. So we can find out how many of these there are. So nearly 13,000 different graphs. However, these graphs are more the type that mathematicians and graph theorists are interested in, and they're not necessarily representative of some kind of real world network. So for that, if we want a real world network, we use the example data, the Wolfram data repository, where there are lots of example network graphs, basically. So how many of these are there? 228. So there's lots of example networks for us to choose from that have been collected, and they're in the Wolfram data repository. Okay, so that's if you didn't have your own data, that's where you'd get an example network from. But if you did have your own data, you can import it directly into the notebook. So this is a common graph or network file type .col. And if you've downloaded the notebook, you should have also downloaded this additional file. So we can just import this, and straight away we have a graph. Okay, if we want to visualize this, we can use graph plot. And straight away, I think this might benefit from being visualized in 3D. So I'm going to use the function graph plot 3D of this object here. Okay, there we go. Okay. If we get time, I'll show you an example that I've been able to make using something I use in my own personal note taking. But if we have time, we'll get to that at the end. Okay, it's these kind of graphs in the example data that are really useful for this webinar today, because they represent real world applications. Okay, so we'll be looking at more at this. Okay, let's look at another way first that we can essentially generate graphs using Wolfram Language. I'll show two ways on this slide. One is using a uniform graph distribution, and one is using the Bernoulli graph distribution. Okay, so this first one, we'll look at what's going on here from the code, and then we'll visualize it. So there are finitely many graphs with 60 edges and this many nodes. Okay, and what we do is we make a random choice of all of the graphs that have that many edges and that many nodes. And then we're also ensuring that this graph is connected. As you can see here, while the graph is not a connected graph, we'll make a different choice. Okay, we can actually find out how many this is. So 126. So we're going to have 60 nodes and 60 edges and 126 nodes. No, I was right the first time. Yeah, 60 nodes and 126 edges. N vertex M edge. I've just used the drop down here to check the documentation. So yeah, 60 vertex, 126 edge. So let's see what this looks like. Let's see what our random choice does. So this is the one it's selected. If we ran it again, maybe it would select a different one. There you go. Okay, I have a question here from Michael, who says, what does the @ sign do? Good question. So the @ is just a prefix form of how you indicate that you want to apply this function. And what do I mean by that? I can replace @ with simply the standard square bracket, and it's the exact same thing. Okay, so just this is a brief aside, but you can write functions in 3 different ways in Wolfram language. You can use the square brackets, you can use f @ x, and you can do a postfix, which is you take x and then you want to evaluate f on x. Okay, it's important to know these 3 things because you may see them cropping up. If you're just starting out, I would stick with this. Thanks for your question. Okay. So, as we can see, we've generated a graph with this many nodes and this many edges. Okay. Now, the second, we're going to generate graphs in a slightly different way. So this is using the Bernoulli graph distribution, where we start with 60 nodes, 60 vertices, right? And then we have some probability of a edge being kept or discarded. I'll try to explain a bit more clearly what I mean here, because the graph starts off as complete, which means every node is connected to every other node. Let me show you what this looks like for, 8 nodes or so. So this is what it looks like for 8. This graph gets very busy as you increase the number. So here's what it looks like for 30 nodes, where each of these nodes is connected to every other one. Okay, so that's what we start off, but we have 60 of them. So you can imagine how busy this graph gets. And so we start with a complete graph with 60 nodes, but we have this edge probability p, which in this case is 1/14. And it's like we start with all of these edges, and then we take each edge in turn, flip a coin, which in this case is not a 50-50 coin, it's a 13/14 to 1/14 coin that decides whether or not we keep that edge. Okay, and the result is this. Okay, so clearly this is not a complete graph. You can actually find out how far away it is from being complete using the graph density function. There you are. In fact, this is quite similar to 1/13, as you might expect. Okay. So yes, these 2 distributions are incredibly useful, but when you're doing network science, there are other distributions that may be more applicable to like real world problems. Okay. One problem that these 2 distributions have is that all nodes are treated equally, which is not necessarily appropriate for certain types of network analyses. The example that's often given is that one celebrity's social media account cannot be treated as equal to all the accounts of their millions of followers, etc. And you can look at the documentation of these graph distributions as well. So Duard has asked if the font size can be increased. Yeah, I should be able to do that. Okay, usually I can just access the toolbar, but I think with this presentation mode, I can't. So I'm sorry, I seem unable to access the toolbar. Anyway, we'll just continue from where we left off. So Jim F has asked, what are the use cases for generating random graphs? It's a good question. Graphs like these that are sampled from these distributions, I believe they're used a lot in kind of mathematical proofs, because it is a kind of idealized scenario where you don't have to treat any given node as special. Yes, so I suppose that's one example I can think of straight away, but yes, it's often difficult to try and find use cases for graphs and networks that aren't explicitly already representing a use case. Wolfgang has asked, is there some graph database working under the hood with its own GQL? I'm not sure. That if you can find out the answer to that, then I'd encourage you to look on maybe Wolfram, like Mathematica Stack Exchange or something like that. Okay. Right. So let's look at a distribution that actually differentiates between nodes. So the issue with the graphs from the previous distribution is that the vertex degrees are normally distributed, right? You kind of get this normal distribution in vertex degree, and a vertex degree is how many edges are incident into that vertex, okay? So this is the kind of distribution you get for these uniform graph distribution and the Bernoulli graph distribution. Now, if we want to break this symmetry between nodes, we need to use a different distribution. And the one we'll use today is the Barabasi-Albert graph distribution, also known as the rich get richer distribution, okay? This kind of, you can reduce this down to like when someone joins a social network, they are more likely to follow someone who has more followers already. Okay, and this is what this looks like. And we can plot this similar kind of histogram as this. Okay, and it can be shown that the fraction of nodes that have a degree k is inversely polynomial in k. It kind of follows a power law. And these are called scale-free graphs. Okay, so you can see this distribution, it's much different than this. And if I changed, well, if I change the parameters of the inputs to this Barabasi-Albert graph distribution, then we'll get a different histogram here. And the way this works is that at each step, a new vertex with a certain amount of edges is added. And these edges are attached to vertices at random. And what happens, it follows a distribution proportional to the vertices degree. Therefore, if a vertex or node already has a high degree, then it's more likely to kind of obtain additional edges. Hence the rich get richer idiom here. Okay, so you know, you can kind of increase this number from 3 to 4, and you'll see the distribution get a bit different. You can also see how running this multiple times doesn't necessarily always give you the same graph. In fact, by definition, the randomness involved here, it will give you a different graph. But you can see how steeply the degree kind of drops off. So let's move on to another real world network. So I mentioned graph density before. It's essentially a measure of how connected a graph is. Just to make sure you know what this is, the graph density of a complete graph is always 1 because every node is connected to every other node. Okay. So we'll take a very famous example data set that is a network. That is this. You can look it up if you like. I won't go into it in too much detail, but it's essentially, it measures friendships between members of a karate club that a person called Zachary went to. All right. So we'll look at the graph density of this. It's about 14%. And maybe there's some drama that plays out over time, causing a change in the friendships and relationships in this network. So we're going to visualize that with list animate. And in one of the final slides of this presentation, it has some initialization where this drama has kind of been constructed. So if you have the notebook, you can kind of scroll to the end and see how this was done. It's really just deleting some edges in a kind of dynamic way at each time step. But let's animate this. Okay, so you can see that some edges are becoming connected, some of the connection is being deleted. Okay, and then you could plot this against time, right? You could plot some measure of the connectedness of the graph, like the graph density, with time. And maybe this would give you some measure of, like, I don't know, the social health of the karate club. So this appears to be going down, this animation that we generated. Okay. So now we're going to look at finding cliques and communities. There's one slide before that that's graph reciprocity. That's another metric. So this is the fraction of edges that are reciprocated. This is also called the number of 2 cycles. So when edge A is connected to edge B, and edge B is also connected to edge A. Okay, I can pull up the documentation of this. Okay, so for a directed graphs, the edges U goes to V and V goes to U are reciprocal and form a cycle of length 2. Okay? So edges like this would contribute to the reciprocity, whereas edges like this would not. Hopefully that makes sense. So I really like this example because it builds on something really intuitive to those of us that are familiar with mathematical proofs. One of the networks in the example data repository is Euclid's Elements. Okay, and one of my colleagues actually worked on this project, kind of establishing a graph of proofs starting with Euclid's initial axioms of how you then went on to prove hundreds. Okay, and the kind of path in mathematical proof space you take to prove certain things. So let's look at what this graph looks like first. So here we are connecting to the Wolfram data repository, specifying that we want a network graph that is called Euclid Elements. Okay, and here's what it looks like. And if you zoom in here, you can see that these edges are in fact directed. So these 2 edges being reciprocal would be indicated by an arrow, like this arrow, which we have, but then also we'd have an arrow going back here. And straight away, given that we know these are, geometric proofs, you can't prove something and then use the thing you proved to prove the thing you used to prove that thing. I know that's a bit of a mouthful, but this is encapsulated in the graph reciprocity being 0. Okay, there's no cyclical proof. You can't make a cyclical proof. So I think that's a really nice example. I'm happy to clarify what I mean if that wasn't fully clear. And then we'll look at the graph reciprocity of some other data sets. So here, this graph tracks the papers cited in complexity theory. And we want to pose the question, is it possible for two papers to cite one another? Intuitively, it shouldn't be, right? Because papers are kind of published sequentially. If one paper is published before another, then surely they can't both cite one another. But we do find out that it's a very small percentage. And this is just because some papers are updated, okay? And maybe they were released and then updated, giving them chance to cite a paper that was actually published after them, after the original. Okay, we can also query things like the long description of these graphs. Yeah. I believe it starts to come up with an option as well. Oops. Yeah, straight away. So we're given lots of options that we can start to choose from because these are all named. Curious to see what this is. So let's look at the description of the jazz musicians. Okay, doesn't actually tell us that much, but this is a network of jazz musicians, whatever that means. Cool. So go ahead and look at this. All right. If you don't necessarily have the notebook and you want to just go straight to the source, then you can go to the data repository and look at these, yeah, on there. So here's the site for the data repository, and I've just searched the term network, and then you can see all these results that come up. Great. Okay. So in a network or a graph, a clique is a set of vertices that are all connected to one another. It's the strongest possible definition of a community. Okay, so in the initialization, we've defined a friend graph that looks like this. This next line of code, it just kind of shows you how to, a different way of visualizing this graph, because you can start at a given node, in this case, Olivia, and kind of see like an organizational chart from the point of view of Olivia at the top. So this is what that looks like. It contains every node. It just doesn't contain every edge. It only contains every edge insofar as it relates to Olivia. Okay, so now we're going to use the function findClique, making sure that we select only the longest ones. Okay, so it defines these cliques, 3 of them. Notice there is some overlap in these cliques, and we're going to visualize this using this very helpful function, highlight graph. Okay, so it's highlighted the cliques using different colors. Jonathan has asked, can the notes be more spread out in the graph? In other words, can you change the spatial arrangement of the notes on the graph? I'm not sure what you mean by notes. Do you mean labels of vertices? Okay, so here are those cliques visualized in different colors. That's what highlight graph has done. And we can see that we've got a clique here in red, we've got a clique here in black, and then we appear to have Oh, in fact, I've just realized the black clique isn't a clique at all. It's those nodes that weren't identified as being in a clique. Sorry. So yes, we have a clique in red, a clique in purple, and a clique in yellow. But the interesting thing is that the purple and yellow cliques only differ by one node. And you can see that in here, okay? It's only Noah that isn't in this one, and it's only John that isn't in this one. So straight away, you might ask yourself the question, if these two cliques are only different by one, then maybe it doesn't make sense to use that definition of a community to define a community. Okay, we may have to come up with a less strict definition. Or a more forgiving definition of a community. Okay, Jonathan meant the vertices. Spread out. So maybe you mean like a different kind of orientation of the graph, like which is called embedding. You can actually arrange the graph to be visualized in a different way, and we will get into that. So hopefully that later on in this talk, your question is answered. And Ajit has said, can you please define clique? Yes. So remember how before I showed what a complete graph is? You could think of a clique as a kind of locally complete graph. So in this case, Fatima is connected to Guy, Abigail, Elvis, and Maria. Same for Elvis, he's connected to all of them. So this kind of, in fact, let me show you the complete graph with 5 nodes. Can you see how this is analogous to this kind of cluster over here? So these 5 people are in a clique. Okay, maybe looking at the documentation of find clique might even make this definition even clearer. A maximal set of vertices where the corresponding subgraph is a complete graph. Excellent definition by the documentation. Yeah, hopefully that answers your question, Ajit. Okay, so new definitions of communities, that's what we're after. So one of the ways you can do this kind of without much manual work yourself is to use community graph plot. So this is what we get when we use this. You're essentially just employing this function to identify communities for you that don't necessarily correspond to the strict definition of a clique. And this community graph plot, as with lots of Wolfram language functions, has methods, has explicit methods that you can state. Okay. So these two methods actually give us the same communities. Yes, they do. It's just not amazingly clear to see because they've used slightly different methods of getting there, but ultimately they've gotten the same result. Okay, there are lots more methods this can take. This method called modularity, what it's trying to do is maximize the weight of edges falling within a community. And sometimes what this does is that you get disjoint communities, kind of where this node doesn't necessarily seem like it's going to be in a community with these nodes, but this method has found that it is according to that method. Okay. And I want to kind of show you how sometimes the choice of method is really important, because this method, clique percolation, allows it considers 2 cliques that differ by 1 element, like we found before, as in the same community. But it kind of does this in a way that as soon as you have two that are considered in the same community, then maybe they are sufficiently connected to more and more nodes, such that you keep adding more and more nodes to the same community. And eventually your definition of a community is so diluted that every node on the graph is considered to be part of the same community. So obviously this isn't useful, right? Okay. In this case, I should say, sometimes it is useful. For example, here we've used the clique percolation method to identify, I suppose, yeah, we have multiple communities here. That have been kept separate despite using this method. Okay, this is the Zachary's Karate Club example data set from before, which we will revisit at the end of this talk as well. Right, okay, so that was a bit of a discussion on cliques and communities. And yeah, obviously any questions, just ask away. I suppose it's important to kind of identify that, you know, you can just give the graph to some built-in Wolfram language function like community graph plot, but maybe sometimes you want to be a bit more explicit in how communities are identified, okay? In which case you'd use a specific method. So this next section is just talking about how we can annotate our graphs. This first example, we annotate the graph using built-in styling functions like edge labels. Okay, so, you know, we've specified a edge weight that is a random integer. We've used the function grid graph, so we have a 7x7 grid as our graph. And then the edge labels are just the edge weights. Okay, this is pretty simple. I think we've seen this before. However, you can also supply your own custom annotations using the function annotation and then retrieve them again using annotation value. So if anyone is familiar with football teams in the UK, then I believe what's going on here is that someone has taken the two Sheffield football teams, Sheffield United and Sheffield Wednesday, and maybe they're making some kind of combined team out of the players of both teams. It's not exactly that intuitive, but really this is just so we can see how to custom the labels on this graph, because the annotations are specified by team, and team is a random choice of United and Wednesday. Okay, and then when we actually come to plot the graph and label it, we say that the vertex V has an annotation value corresponding to one of the choices of team. All right. In preparing for this talk, I was thinking, I can run this again, and obviously it will make different random choices. And, you know, I never really played this, but in FIFA, you represent chemistry, I believe, between players as a kind of, that's really assigning a weight to an edge of a network. Okay, so you can see this stuff everywhere if you kind of know what you're looking at. Thomas has asked, do you have the Louvain community detection or Gervan Neumann method? Good question. Maybe I'll have a look in the documentation. I don't know off the top of my head. But... So if we go in the details and options section, and then we look at method, we can actually jump to the examples that use method. I believe the examples only contain the more common methods, so maybe it's in here. Doesn't explicitly say. Sorry, Thomas. Yeah, it's not limited to the methods shown here, but it doesn't give an exhaustive list. Oh, but here it does. So here in the function find graph communities, we have these possible settings of the method. So I believe the one you mentioned isn't there, but thanks for your question. Okay, the next thing I want to talk about is more graph metrics, specifically homophily and assortativity. So network homophily refers to a theory in network science that based on the attributes that nodes have, similar nodes are more likely to be attached or connected than dissimilar nodes. Okay, this kind of makes intuitive sense. So here, this network is representing a school where students support different football teams, and an edge between two nodes indicates that those two people are friends. Okay, so we're going to define this graph as G. So there's 3 different football teams here. And then maybe you want to make some tests on this graph, right? Here the question is phrased as, does extroversion predict cohesion better than the team you support? Now, what does that mean? Well, how social a student is, maybe how extroverted, we can measure that by the degree of the vertex. Okay, like how many friendship connections they have. Now, linking this to the idea of homophily, this would be nodes that are connected, provided that they support the same team, so that they are, colored the same here on this graph. Yes, and assortativity is this measure of like the tendency of nodes in a network to connect with similar ones. Okay, so in the first function here, just the graph assortativity, it's measuring assortativity based on the degree of the node. So essentially, it's like, to what extent do students with similar numbers of friends cluster together? Does that make sense? So like the friends, people with lots of friends are friends with other people with lots of friends. So this is a kind of assortativity based on just the vertex degree. Okay. Now the next one is the graph assortativity of this graph, but with this extra argument team. And this is measuring assortativity based on which team you support. So here we can actually see that the assortativity based on purely how many friends a given node has is higher than the assortativity based on which team you support. And that's not that intuitive because, especially when the colors are the first thing that hit you about this graph, right? So you might think, oh, well, of course, people are going to be friends with people who support the same football team, perhaps. But there's actually some deeper relationships kind of encoded in this graph. And you can measure these using functions like graph assortativity. Okay, hopefully that makes sense. And then this next section kind of just goes into graph assortativity and how sometimes it can tell us no information and sometimes it can tell us some information. It's an informational quantity. So we start by considering a complete graph. We know what that is by now. Team A, where everyone is friends with everyone. Everyone is on the same team. Okay. Again, we're back to the two teams of Sheffield here. So here's what it looks like. But despite the fact that based on our definition of assortativity, you think, okay, this graph is very connected, and they're all supporting the same team, so we can find the assortativity. But when you actually run this function, you get 0. And really, this is because, how should I say this? There's no mixing pattern to detect because all nodes are identical in terms of the attribute you're testing. Okay, so what we need to do, how to get around this, is we define a graph that is kind of two disjointed graphs, one for one football team and one for another. So whilst it kind of outputs one on top of the other here, these are the same graph, just disjointed. Okay, and now when we find the graph assortativity on the graph represented by both teams, we get 1. Okay, so two separate homogeneous groups have yielded perfect assortativity, provided there's no kind of edges that connect the two groups. So maybe I could try and make it so that there are. Yes, here we are. So I've just changed one thing in my code, and now we have this kind of this rogue player that has made friends with some of the other team. And we have a non-zero assortativity. Okay, and now I've just changed it back. But this is good. I think we're really getting into the root of how you can start to draw some insights from real-world networks. Okay, so the next section is about centrality. I don't think I want to spend too long on this, but this is one of those paradoxes I talked about before, where it's called the friendship paradox. And in short, it states that you are more likely to be friends with someone who has lots of friends on average. Okay? This is one of those things where as soon as you get your head around it, you start to kind of see it everywhere. You start to see where these kind of sampling biases that we all are subject to start to interfere with our lives, I suppose. But what we're doing here is essentially proving that for this case. So we take a random graph from the rich get richer distribution that we used before. We find the mean degree of each vertex, 5.8. We define a function which gets the neighbors of a given node and then gets the mean degree of those nodes. Okay, so here we're just defining functions. And then we use this function on all of the vertices in the graph and then find the mean. Okay, and as you can see here, it's around 8.2, so it's significantly higher. And I want to emphasize this is true for strictly all graphs with any variation in degree. It's not just because we use the rich get richer distribution, although perhaps that exaggerates the difference. So yeah, that's a fun one to tell your friends. So centrality. Centrality is all about how you take one individual node and then have some measure of how important it is or how central it is. Again, we come back to this Zachary's Karate Club dataset. And then what we're going to do in this slide and the subsequent slides is just use lots of different measures of centrality. So we've got this function show centrality, which is defined in the initialization. I'm just going to go straight to it. It's defined here, show centrality. And it just highlights the graph based on that definition of centrality. So this argument, cfun, is our centrality function that we're going to use. Okay, so we'll start off with degree centrality. So this is perfectly fine, but here it says a bit naive. Measure of centrality would be the degree of each vertex, right? So this is what we get. And let's use the same measure of centrality, degree centrality, on an example graph. So you might spot some issues with this. First, let's look at example graph. This node number 21 is clearly central, but because it's only got a degree of 2, it doesn't rank very highly on this measure of centrality. Okay? So how can we build on this? Intuitively, node 21 is central because it is a node you must travel through if you want to traverse the graph. Okay, if you want to go from here to here, you must go through node 21. So this next measure of centrality is called betweenness centrality. And this is a measure of whether the node lies on more shortest paths. Okay, so here we are. The node is more represented in this measure of centrality. Okay, and here we have closeness centrality, and this seems to be even more appropriate for this graph. And then here we're just making an association between the centrality measure and the vertex list. So we're going to see how 21 does with this measure. And as you can see, 21 just about beats vertex 1. And then obviously there's costs and benefits depending on your choice of centrality, and that kind of goes into that here. Looking at the differences between, for example, closeness centrality and betweenness centrality, where in betweenness centrality, a shortest path is counted with weight 0 or 1, whereas in closeness centrality, it's counted according to the weight of the path. Okay. Yeah, so for the Zachary Karate Club network, closeness centrality, maybe it's not as useful. And I could probably go on all day about this. So here's one final measure of centrality, eccentricity, which really emphasizes the node 21 in the center. And I can actually use this function ** centrality, which will show me all functions that contain centrality. at the end at least. And here they all are. So there's lots here. And what's cool is that you can see the system functions, and then you can see the one we've defined, which is considered to be in the global context. Now, those of you who are familiar with Wolfram Language, maybe you can envisage like a super function where there's some, I don't know, decision making behind the scenes where the Wolfram kernel just kind of chooses which centrality measure to use. A bit like with classify and predict, these Wolfram language super functions, which classify, these automate the process of choosing the machine learning algorithm. Now, I can envisage a similar kind of super function for finding the centrality of a graph. It's kind of interesting to think of like the progression of programming languages as just being more high level and declarative, where, well, back in the day, maybe you had an algorithm and you said, okay, I've got this algorithm, maybe I can implement that in this programming language that's quite low level, like C or something like that. And then you go one level above and it's like, okay, I have this collection of algorithms. Which one should I choose? And then you choose one. Wolfram language is arguably the largest collection of algorithms in the world. And then the super function idea is kind of a step above that, where you say, I just want to do something. And then the tool that you're using automates the choice of algorithm to get you there based on the specific scenario, which in this case is a network. So it's fascinating to think about. And sometimes you'll need more control over this automation. Sometimes you can let the machine choose. Anyway, I digress. We're going to finish off with a discussion of flow in networks, and then that should leave us some time at the end for questions. So let's set up a graph which has some directed nodes. Okay, they don't necessarily have to be directed, but they will be in this case. And we've also labeled the source and sink on this graph. Okay, so the source is here, the sink is here. And these edges have, no, not these edges, these nodes have weights, which you can kind of think of as a capacity that the node can hold, right? And what we want to do is find the maximum flow that you can kind of push through this network. Okay, and in order to do that, you could spend hours pen and paper doing it, or you can use this function find maximum flow. Okay, now we've asked for the optimum flow data, and we can query this by just, well, first asking for its properties. So we have all of these properties, and we know that we want the flow value, and then we want to visualize this flow value on a graph. So here we are. So here, what this is telling us is that the maximum flow value is 3. So you can't get any more than 3 arbitrary units of flow down this graph. And I also want to show you how, perhaps I can delete some edges here. So maybe I'll delete this edge and this edge. Now the graph looks different. We run this function again. And this time we have a maximum flow of 2. Okay, very basic example, but hopefully you get the idea. And what we want to do now is kind of scale it up to quite a detailed example. And this is a railway network that I mentioned earlier of the Western Soviet Union and Eastern European countries in 1955. Okay, so here's the image. It's a magnified version, you can see that we have all of these are considered like origin stations. And then maybe we have some like target stations here. Yes, and these edges are labeled, and the nodes are labeled as well. As I said before, maybe this corresponds to some maximum transportable quantity of, I don't know, machinery or goods. So the tedious process of converting this image into a graph has been done for us, and we can so we can represent that graph now, which it looks like this, and then we can overlay that onto the image. So this is a blurred image. The sources have been indicated in green and the sinks in red. I can just reduce the blur a bit so you can see it a bit clearer. You can see that it very nicely replicates it. So that's pretty cool. Okay. Now we want to find the maximum flow. All we need, now we have the graph and the edge weights and the node weights, which are all kind of specified in this thing that's been iconized. We can just specify which nodes are the sources and which nodes are the sinks, and then run this function. Okay, and we get the maximum flow that's measured in thousands of tons, and it's 163. So really, I mean, the fact that these two problems are equivalently easy, provided you use these built-in functions, it is quite impressive. And the next thing I'll talk about is the minimum cut theorem. So, you know, I'm not entirely sure of the history of this this particular example, but perhaps some opposing army want to sever the network so that sources and sinks are cut off from one another, and you know, you can no longer deliver goods. This is just like making a cut through the network, and you do this using the function find edge cut. Okay, so just looking at the drop down here, this is going to find the smallest edge cut of the graph between nodes 13 and 44. Now, where was node 13 and 44? I'm just going to go back to the other slide. Yeah, so from here to here. So the reason we only got a cut that was here, like this isn't exactly helpful because it doesn't take into account the rest of the network. And that's because we've got multiple sources and multiple sinks here. And what we need to do is basically construct a super source, which is the source of all sources, and a super sink, which is the source, sorry, the sink of all sinks. Okay, and then, yeah, this is what we do here. So here is our super source, and here is our super sink. These are actually assigned infinite weight, these edges, to make sure that the cut doesn't go through them. Because, you know, if you were to place a cut through here, then you just have your whole graph to the left of it and nothing to the right of it. So it's completely meaningless. Okay, this allows us to use the find edge cut function. This time we're specifying between S and T. And then thanks to highlight graph, we have actually highlighted in red the edges we must cut through if we want the minimum cut. So this is really cool. You can see the cut would be kind of here. All right, excellent. Okay, this last section is drawing your attention back to this karate club graph. And then there was, apparently this is real. There was a pay dispute between an instructor and an administrator, which tore the club in two. These are the nodes corresponding to those two people. And then what we want to do is predict how this kind of fission of the graph will look based on the assumption that people tend to follow their friends. Now, people tend to follow their friends. That's a sentence that, that you can understand with words, but really putting your graph theory network analysis hat on for a second. We're looking for a minimum cut there because we want to destroy as few friendships as possible because people have followed their friends. You know what I mean? Like, it's really helpful to be able to like assign algorithms or like processes to these kind of generic intuitive phrases and sentences. So really, it's just the same thing as the railway example. We're using the find edge cut function between these nodes 1 and 34, representing these two people. So the cut tells us which edges to delete, and then we'll use edge delete to delete them. And here's our two graphs that remain, that are the result of this fission. Okay. So we've kind of formed two new clubs based on this fission, and here we're just defining the nodes that are in these two groups using this function connected components. And then we actually have here this list that has just been manually inputted. This is the actual group that formed around one of these, I believe the instructor. And we can use this function symmetric difference to find out like how different this is from the result of find edge cut. And we can see that it's only the node corresponding to person 3 that we didn't capture in our fissioning, as it were. So as you can see, the algorithm did very well. Not 100% well, but it was a somewhat accurate description of what really happened in this network. Okay, cool. Yes, I use this symmetric difference function a lot, actually, just to measure the the symmetric difference between two lists. And with that, I think we're out of content, so I will stick around for questions. And we have some resources at the end of the notebook here. And